The second speaker is Professor Hyeong-Chan Kim from Korean National University of Transportation. He will talk about heat conduction in general relativity. So talk time is 25 minutes, so I will let you know 10 minutes before finishing. Okay, so go ahead.
Okay, thank you for the introduction. So, as you see outside, it's going too hot, right? The sun is hit us now. So, I study heat conduction in general relativity. with 마스크. 감사합니다. With Dr. Young-won Lee. Okay, so the main problem is starting from the thermodynamics is based on Gaussian profiles. And in Gaussian profiles, the velocity, the speed of the particles in thermodynamics is distributed from zero velocity to infinity velocity. So based on the distributions, the information may travel with infinity speed. This makes causality problem, of course. So we need to care for this. So let's begin with the Newtonian theory of heat propagations. The heat equation in the Newtonian theory take this composed of these two equations. First says how the heat propagate. So it says that the gradient of the temperature, when the temperature is different for two nearby places, there appears heat. The second equation is then how the temperature changes. It says that when the heat, the sum of the heat coming to a point is non-zero, then the temperature changes. Combining these two, the resulting heat equation takes the form, parabolic form, making the causality problems. Therefore, in the original theory of thermodynamics, information propagates with infinity speed. To cure this deficiency, Cateno and others introduced a small positive time parameter here like this. He added to the heat equation, to the left part of the heat equation, he added this part manually. And this makes the system hyperbolic and restore causality at the cost of introducing a term, this term that does not come from some underlying microphysics. Now, we can go to the relativistic theory, relativistic analogy of these Catano equations. Usually, in the literatures, the derivation of the Catano equation goes like this. First, write the time part energy momentum conservation law. Then, the time part of the energy momentum conservation law usually takes this form. The left-hand side is the entropy creation rate, and the right-hand side, usually it takes some complex form, but if we summarize it, has like this form, the Q, the heat flow vector times HA, some spatial vector field consisting of thermodynamical quantities. Now, because the entropy should be non-decreasing, this rate must be non-negative. To achieve this purpose is to make this creation rate part to be proportional to Q square. So the relativistic analogy of the Cataneo equation goes like this. Just write the heat to be proportional to this vector HA by setting this form. Then we get the creation rate to be the Q, to take the form of Q square. So for comprehensive review of this relativistic hydrodynamics, see the paper and the review paper of Anderson and Koma, 2021, just a recent one. However, we can easily notice that any addition of Q vector, Q by normal vector, which is normal to both Q and the particle flow lines, does not hurt the present argument. Therefore, we notice that there are two additional degrees of freedom in the choice of heat flow equations. And in fact, this fact was known implicitly, but no one studied yet. So we studied this possibility thoroughly, and we find that it has a very important role in the relativistic thermodynamics of heat propagations. So there are two approaches for relativistic thermodynamics. First is Israel-Stewart theory. It's a kind of legs or just a correction of the phenomenological theories. So it begins with Eckhart and Stewart and Israel-Stewart, and so almost finished. Almost full formulation was done in 1979. On the other hand, the other approach is the action integral approaches. It begins with Taum in 1954, but its formulation was still undergoing. But now in almost we have almost we have a good formulation in 2015 now. So anyone, you can wear anything. But in my case, I prefer this path. So I go with this. So the formulation goes like this. We think so matter space in three-dimensional matter space. So the coordinate on this matter space we write like capital X. From this matter space, we can define some three-point field N. This three-point field must be a function of X only. Then we can map from this matter space to the space-time, coordinate space-time like this. Then this coordinate X is just becomes a function of space-time coordinate X. So we introduce three scalar field X. By this, the point in the matter space, becomes the particle trajectory in a space-time. Then we can write the three-point field in this matter space three-point field. By using this mapping, we can define a three-point field on space-times, like in these forms. And from this, by using the volume form, we can define a vector field N. Naturally, then we can calculate the exterior derivative on this matter space like this, and this naturally gives us the exterior derivative of N on space-time, and it naturally give us this gradient of N equivalences. And this is a quite familiar formula for us. We can interpret this N as the particle number, and this is just nothing but the particle number conservation. So we begin with this approaches. So particle conservation is a natural consequence of this construction. because there are many fields in our universes, we can introduce many kinds of particles. However, for simplicity, we introduce two fluid models. So we introduce two matter space. One is X. This is the number density in this particle X. We can write N. And the other is the Y matter space, and the matter residing in this matter space we call SA. So we will call this N is the number space of the matters of the particles, and S is the caloric flow. So it is a kind of entropy flow. We will denote that. Usually, the two matter space are not parallel. So that will call the usually entrainment, and it has big consequences. So the flow lines of the fluid sometimes overlap with each other. In that case, we can make interacting matter space pictures. So like this, and ABC, the three-point field residing on X space may depend both on X and Y. Okay. So the action formalism for thermodynamics goes like this. The mass function, just nothing but the Lagrangian of the system, must be a function of scalars made of the two fluids N and S, and we have three scalars. One is S square, and the other is N square, and then finally X is S dot N. So we have three scalars S, and therefore the action takes this form. So action is, here is the volume integral, and the mass function is the function of these three. Now, let us introduce a coordinate or a vector field U along the flow line of the particles, along the trajectory of the particles, a unit vector U. And then using this unit vector, we can write the caloric flow SA in terms of this unit vector, SUA plus Q. So this Q is denoted the heat vector. So this Q is the heat vector, and this theta is nothing but the temperature. From the construction, Q and U is normal, also one are always. S is nothing but the entropy density measured by a co-moving observer, and is the number density. With this construction now, the Lagrangian is function of N and S, NS and Q. Therefore, variations of the Lagrangians, but the variation of the Lagrangians give us, takes this form. Here is delta S, the caloric fluid flow vector, and its coefficient is temperature covector, and here the N is the number flow vector, and its coefficient is the chemical potential covector, and this part is contributed to the stress energy tensor. So the temperature covector is, so the U direction part is just we will call the temperature, and this part is just the contribution to the heat, and the chemical potential covector is also the U part is just the chemical potential, and the other part is along the direction of the heat. And this nu is okay, this is not important, so let's go. Then we can derive the variation of this N and S starting from the constructions. So I will not show the details, but just write the formula. Just use this formula. Putting this formula, this variation formula to this delta lambda, we get the variation of the action integrals, and the action integral, the variation of the action integral takes these forms. So this part is stress tensor take these forms. becomes this the temperature covector times caloric vector, right? And pressure, this phi is just the pressure. And the pulse term F0 and F1 is just this one, F0 and F1. So yes, so there is some boundary terms, but it's not important, so I hide it. Here, C part is just the variation, the variation of the prolite by this part. Now, the energy density. We can calculate the energy density from the stress tensor, then it just simply goes like this. So we can interpret this energy density relation as the Lagrange, it's called Legendre transformation from lambda to rho. So because we know the variational relation of the lambda from the previous slide, we can write the variational relation of the rho, energy density rho, like this. Then this is the same as nothing but the first law of thermodynamics. So from this relation, we can interpret theta as temperature and chi as the chemical potential, and this is the conjugate to the heat, right, theta. Okay, so now we have physically sound interpretation for this thermodynamics. Now we are going to determine the dynamical equation of motions to determine all the variables. So we have now 8 thermodynamical variables evolve with times, just the S and N. So it is S, N, and S, the number density, entropy density, and the direction of the particle flows and the heat. So the dynamical equations begins with the first laws, the Bianchi identity, the energy momentum conservation laws. If we explicitly calculate the divergence of the stress tensor, it just write as the sum of the two forces, F0 plus F1. So this first law equation simply says that F0 and F1 act as if it is the action and the reactions. Then the energy momentum conservation law gives us first the U part. The number flow part of the energy momentum conservation law gives us the creation rate both of the S and the creation rate of the particle creation rate. The two combination is given by the heat times U d theta, and the entropy part, the S part of the energy momentum conservation law becomes the also gamma S plus gamma N, and this also these combinations. Yeah. Now, from this, we can write the creation rate of the entropy and the creation rate of the particles. We can obtain from like this. So, as seen in these equations, both vorticity of the caloric and number flow contribute to the both creation rate. Contrary to the previous approach in the literature, we does not set gamma n equal 0. We keep gamma n alive until the times. Okay, let's proceed. So how much time? Okay, so now I will go as done in the previous as did by others. So the creation rate of entropy gamma S takes this form. From this, we can write the heat Q, because this should be should be positive definite, should be non-negative. So we can write the heat Q in general like this form. But we should add Q binomial part Q part here. This is a new degree of freedoms. Now, with this choice, we get the creation rate of the heat as a Q square forms. So now we satisfy the second law of thermodynamics. Like this. Here is the binomial surface. The heat flow along this, and this complex mathematics give us some vector field like this, and this large Q part, the binomial vector, makes it projected to the Q directions.
So you have 5 minutes.
Oh, only 5 minutes, I see.
Okay.
So the second heat equation is just starting from the gamma n, the particle creation rate, and it gives these relations. Combining the two, we get a rather simpler form for the heat equation. First is these two relations, and the binomial part of the energy momentum conservation law gives another equation. Well, this is the binomial part. So we can check for degree of freedoms. We have now 12 independent degree of freedoms, including Q and Q tilde, but we have 10 equation of motions. So we reformulated the relativistic analog of the Catano equations in the presence of particle creation rate. Therefore, the heat flow equation hold even in that case. We studied the heat flow equation in a general form by introducing of binomial vectors. Because of it, two equations of motions are missing. So we can interpret it as present a room to impose reasonable physical conditions. So let's begin with the thermal equilibrium. For the thermal equilibrium case, but the particle creation rate vanishes, entropy creation rate vanishes, and the Catano equation gives us this kind of formula, and this T is nothing but the gradient theta, roughly speaking. And in fact, if we solve this equation, we get the Tolman temperature relations. So we will call this Tolman temperature gradient. And finally, the method flow equation gives us this Klein relations. So these four equations reproduce all the known property of a thermal equilibrium system. Now, let us determine the binomial vectors. We can get this relation by combining the relation A to C. Okay, so I will proceed. I will haste the procedures. Then the relativistic analysis of Catano equations, explicitly writing, take these forms, and from this, we can find out that when we set this part, this first equation vanishes, then it gives us the choice of the Anderson et al. In 2001. And if we choose the second part vanishes, it gives us the choice of the Carter's. But we know that the Carter's choice is unstable, but the Anderson's choice is stable. Therefore, this implies that the choice of this binomial vector field is physically relevant. It is not a simple case choice. And this is another equation of motions, and this is another. So, because we have replaced the binomial part by using this right-hand side, it appears that we now have 8 independent parameters with 8 independent equation of motions. However, this is not the case, because if we project out this equation, the binomial part of this equation is in fact the same as the previous equations. Therefore, we still lack of 2 equation of motions. To determine the 2 equation of motions, so we can write this formula for the left-hand side is just composed of the Q part, and the right-hand side is just the source part without heat. Now we can think that like this, the heat flow along this line, and we can think two nearby subsystem normal to the heat flow. Then these two systems must be in equilibrium. We cannot say it is somewhere equilibrium, but anyway it is equilibrium. Then we can impose.
Professor. Now will you summarize some result?
Okay.
Yeah.
Okay. So this should be in equilibrium. So it gives we need like this Tolman ansatz, because Tolman temperature relation dictates the equilibrium condition. So I impose this condition. So then we can think about linear perturbations. So I go over. Therefore, we find that the behavior of these linear perturbations are far better than those in the literature. So let's summarize the result. We consider the problem of heat conduction in general relativity using Carter's variational formalism of thermodynamics, and the heat conduction equation is formulated by one relativistic analog equation and one Pohang equation. So two matter. So because of the binomial degree of freedoms, the two equation is not sufficient to describe the evolution of the thermodynamical systems. And we propose to replenish the shortage, we propose an ansatz. Starting from the physical property of thermal equilibrium systems. Then we find that the stability requirement is less stringent than those in the literatures. And I haven't said, but we find new modes, nuclear mode exist in addition to the known ones. Okay, thank you very much.
Okay, thank you. So time is over, but shall we have one or two questions?
I have a question.
Okay.
Okay, so you review and or explore the conduction, heat conduction in the general relativity.
Yes.
Okay.
Yes.
So my question is, where can you use your formalism? I want to know what is your target object. For example, this is just my thinking. If you consider the accretion disk around the black hole, then maybe you can use the heat conduction in the general relativity.
Yes, of course. But where is my formalism? You say from this one.
No. I want to know where can you use your formalism?
So many places in cosmology, for example, we can formulate we can use this thermodynamical formulation even in cosmology. For example,
which area?
Because what is temperature? In a time-dependent system, it is very difficult to define temperature itself. Even in cosmology, we use there is a temperature in here, but how can we define the temperature here?
So maybe I guess that your formalism can be used the heating process in after the inflation.
Yes. And we can also apply it to near black hole or to the neutron star and other things in higher gravity. And we can also apply this formalism in high-speed particles, a set of high-speed particles, plasmas.
High-speed plasmas?
Yes.
Then maybe you can use the special relativity in that case.
Yes.
Then why you can use the general relativity formalism in the high plasma case?
This formalism is also applied to special relativity also, and in the case of the high velocity plasmas, it is very difficult to define the temperature also. But if we use this kind of formalism, then we can naturally define the temperature, because this formalism starts from the vector field. The temperature is generalized to a kind of vectors now. So the temperature is dependent on observers.
Okay.
Okay, yeah, thank you. So because of time, let's finish this talk and then switch to next speaker. So the first speaker is still missing, so it's better to switch to next speaker. So next speaker is Dr. Neo Park from IBS. So she will talk about rectifying no hair theorem in Hounsonian theory.